Hi everyone, my name is Lisa Kelsey. I'm a Lever Hillman Isaac Newton Trust Fellow at the University of Cambridge, and I'm going to tell you a little bit today about what I have done in the past and what I'm currently working on as part of my new fellowship, talking a little bit about the environments of Type Ia supernova, focusing really locally, and what that means for supernova siblings. So we've already seen a plot a little bit like this from Matt's talk. So this is the mass step. Type Ia supernovae are found in all types of galaxy, and we know that the color and stretch-corrected brightness correlates with the stellar mass of our host galaxy, where the 1As in high mass or passive galaxies are brighter than those in lower mass star-forming galaxies, even after standardization, with this offset roughly around 0.06 mag, although this is different in other surveys. But that might naturally lead you on to the next kind of question of, okay, if this holds for entire galaxies, what does this mean when you look more locally at the really close-on environments around the Type Ia supernova themselves? This is one of my absolute favorite props. This is from Mikhail Rogal's 2013 paper, and what you can see here is on the left, both of these supernovae are found in spiral star-forming face-on host galaxies. So you might think, okay, when you're doing your environmental correction, both of these would be on that same kind of side of the mass or color or environment step that you're using. When you actually zoom in a little bit closer, this is looking at some IFU data of those environments. What you'll notice is that one of them is in a region with lots of young stars, lots of active star formation. One is in a region with no star formation with older stars. So if you were to correct these in the same way, you might actually be miscorrecting because one would be on one side of your step and one would be on the other side. And this might mean that, okay, looking locally might give you better standardization for your cosmology. What have people done so far? People have looked at this in some of the big surveys. So we have data from SNLS, we have some from the Supernova Factory and my work in the Dark Energy Survey. We actually found that these environmental steps, when you look locally, are significantly larger than those when you're looking at the entire galaxy as a whole. So that maybe is telling you that that's recovering more information about what is actually causing the root cause of these steps. That's where supernova siblings come in. What are they? There are simply multiple supernova. In this case, for the purposes of this talk, when I say siblings, I just mean 1As associated with the same host galaxy. It was a term first come up with by Brown in his 2014 paper. And how could they solve this environmental dependency? Because they are in the same host galaxy, they share these host galaxy properties and the systematic uncertainties associated with this. So things like redshift, peculiar velocities, and gravitational lensing are shared between these sibling systems. So therefore, any differences that you see in their brightnesses, stretch, colors, Hubble residuals, whatever, has to be due to something else other than the global host galaxy property. This must be either due to subgalactic differences in their environments, dust distributions, progenitor scenarios, explosion mechanisms, you name it, it's something else that is going on here. So this is an example from my recent paper. This is a set of 1A siblings that I found that had the greatest difference in their explosion dates. So one found by Zwicky in 1938 and then one from ZTF in 2020. So how did I start with this work? Let me take you back to the middle of lockdown. I think a lot of us were stuck at home, a little bit bored. I was trying to think up, okay, I need this last chapter for my thesis, something quite exploratory. And I was working in the Dark Energy Survey, and Dan Skolnick had recently put out his paper looking at supernova siblings. And in that paper, he concluded that siblings with the most differing stretch and color values were those that were furthest away from each other, or where one was at the center of the galaxy and one was at the outskirts of the galaxy. And I thought, okay, why don't we look at the local environments? I have the data to do this. This plot is very preliminary. It formed the final chapter of my thesis. But what I found was tentative evidence that siblings with the largest difference in their local masses and their local U-R colors have the largest differences in their overall brightness. However, there are two key issues with doing this work in the Dark Energy Survey. One of those is that the rate of detection of your siblings is limited by the length of your survey. If you're trying to find them all from the same survey, you have a higher rate of Type Ias and more massive galaxies. All of these were high mass galaxies. These high mass galaxies host lower stretch or faster Type Ias, and there's a known correlation between stretch and age. All of these are most likely to come from older progenitors. The other issue is when I say I'm looking at their local environments, a lot of these are at a redshift of around 0.6. So due to the resolution of DES, locally was still quite a large portion of that galaxy. But let me think, okay, what can I do to improve this situation? To solve issue 1, which is the rate of detection is limited by your survey length, I started to look at the archival data. When I started looking at this archival data, I thought, okay, maybe I might find 10 of these such systems. I wasn't too hopeful. And what I actually found was 158 galaxies containing 327 Type Ia supernova siblings, which is a factor of 10 times larger than prior samples looking into this. So I really kind of felt, okay, why is no one looking at this? It's kind of an untapped gold mine here. And what I did was I compared light curve properties between 25 of these pairs of siblings that passed the traditional cosmological cuts on stretch, color, etc., compared to a simulation of false siblings that I obtained from Pantheon data, repeated that a lot of times, and basically tried to compare the stretches and colors between those sets of siblings. And what I found really was that stretch and color are no more similar between Type Ia associated with the same host galaxy than any of these random drawings of siblings. The only thing that was correlated was that was in fact correlated with their redshift. There was a further analysis. What I did was I said, okay, now let's take ones that are at similar redshift and see if this relationship still holds. And even when I compared random supernova at the same redshift, their stretches and colors were still not correlated in any way, shape, or form. That really raises questions about the validity of these host galaxy corrections when we're using Type Ia for our cosmology, and really kind of emphasizes maybe why we should be looking locally instead. The other issue that is currently kind of what I am trying to solve is that issue of the resolution of when you're looking at these really local environments is limited by your telescope and redshift. So I have time with Hubble where I am actually investigating the local environments of a sample of low redshift Type Ia supernova siblings. We've obtained 32 orbits, so we have roughly 28 host galaxies of these siblings. Some required multiple pointings because their locations in their galaxies were too far away for a single HST pointing. And what I am doing is I am working to obtain really high resolution photometry of those local environments to then pass them through a prospector SED fitting code to obtain their environmental properties, compare these to their cosmological properties, and try and understand how these really high resolution measurements are affecting things, and compare, relationships between the local environments and cosmological parameters to define the optimal route to standardizing the 1A. A galaxy that I wanted to highlight, which is kind of the focus of my work at the moment, I'm hoping to put out a single object paper on this very soon, is NGC 5468, which actually hosts 6 supernovae of varying types, 3 of which are Type Ia supernovae. So it was really kind of like a highlight for my analysis to look at these. So yeah, there are shown in dark blue, it's quite difficult to see on the screen. Shown in dark blue are the 2 Type Ias. There's also a 1A peculiar, a Type 2P, a Type 2B, and while my HST data was actually being taken, a 1C decided to go off. Very exciting for me. I've also been very kindly sent some data from Adam Rees's Cepheid program on this galaxy. This also hosts Cepheids. So I have a full 5-color SED that I am fitting using Prospector to determine the stellar mass, metallicity, dust, extinction, and stellar age. And just to quickly show you, what you can hopefully see is the SEDs. These are looking at regions of 0.25 kiloparsec radius around the environment. You can see that SEDs are all very different. And very finally, some very preliminary analysis. I didn't want to share my exact numbers with you guys yet because they are still preliminary. But what you can hopefully see is that the Type Ia that is found in the very outer region of the galaxy has the highest metallicity. And you can see here from its cosmological parameters, it has a very negative stretch value, which is kind of what we expect. The extinction is very similar to that of a peculiar 1A, this 1AX, which is closer in. So we are really seeing that these differences in their cosmological parameters are kind of following on from what we might see in the differences in their actual environment. And yes, the 1AX also came from a region in the galaxy with the lowest stellar metallicity, which is kind of what we expect from these 1AX systems. I will leave you with my conclusions and take any questions you have. Thank you.